Isabelle Chalendar will be talking about spectral properties of weighted composition operators on holomorphic functions on the unit disk.
Many thanks for this invitation. Okay, I start with an introduction. So D is, as usual, the open unit disk. And all D is, as Nicolas said, the set of holomorphic function from D to C. And the topology for this Cauchy space is the uniform convergence on compact subsets of D. Okay, and now we will consider weighted composition operators. So I just need first to define composition. To do that, I take a phi from D to D, which is holomorphic. And I will add a restriction. We assume that phi has a fixed point. And we take the fixed point inside the disk. And there is a usual trick to saying that you may assume that it is 0, and in the more general case, we can mention what happens later. Okay, so we assume that we have that. And then it's a well-known fact that using Schwarz's lemma, it follows that the derivative at 0 is then less or equal to 1. And okay, we assume that it is not equal to 1. So in other words, we assume that we have not a rotation. That is equivalent to say that phi is not a rotation. And also, in order to describe further result, I will assume that the derivative at 0 is not 0. I can mention what happens in this case. It's just in order to make a theorem correct that I assume that, and I will precise what happens in the case where it is 0. Okay. So now we consider C phi. The composition by phi. It is linear and it is continuous with respect to this topology. It's obvious just because the image of a compact is a compact, since phi is continuous. And we had a weight denoted by m. So m is a holomorphic function from D to C. Which is the weight. And then our aim today is to study the spectral property of T which is you compose by phi and you multiply by m. So it's a weighted composition operators. So the questions we are interested in are, what is the point spectrum of T? And what is a spectrum? Okay, so being in the point spectrum, just recall this definition, which is well known, but okay. So by definition, it's just the existence of a function which is not zero, such that Tf equals lambda f, whereas to be in the spectrum is the fact that, so this is exactly the same as saying that T minus lambda identity is not injective. And this is equivalent to say that T, by definition, in our case for the spectrum, it is that this operator is not invertible. Okay. So now we'll recall you what are the known results in this area. Okay, the first known results are concerned with the case where the weight is identically equal to 1. And so let and 0 be the non-negative integers. And now we have a famous result due to Koenig's. French mathematician, long time ago. What he proved is that, so we are in the case where phi at a fixed point and the derivative at 0 satisfies our hypothesis. In this case, what he proved is that the point spectrum of the composition operators defined on the set of alternative function is the discrete set of the powers of the derivative at 0 and the second result is that the limit when you take the iterates with respect to the composition over the derivative at 0 to the n, and here you have n terms. This limit exists in the sense of the uniform convergence on every compact subspace of V. So for the topology on all D. And this function is denoted by, so I denote it by sigma. And these functions, so satisfies that sigma composed with phi is equal to the derivative of phi at 0 times sigma. And the kernel of C phi minus phi prime at 0 to the n is exactly a one-dimensional space generated by these functions to the n. So in other words, Koenig's proved that the point spectrum of C phi is just this set, and the dimension of the eigenspace is 1. Okay, generated by sigma to the n. Okay, so that's an old result. And another known result, more recent, is a theorem due to in a joint work with Wolfgang Arendt. Benjamin Chalendar and myself. What we proved is that, again, in the case where we have 0 as a fixed point and assume that it's not a rotation. In this case, what we prove is that the spectrum of C phi is exactly the point spectrum union 0. So it means that we have nearly nothing else that the point spectrum in the spectrum. Okay, and now I will present a work in progress. So what we are studying now is what happens if we had a weight. So it's a work in progress with my students, Benjamin Chalendar and a new students, Eddie Bernard. Okay, so what we proved is the following result. Again, we assume that we have a fixed point inside, assume that it is 0, it's not a rotation, and we also assume that, okay, I have this condition, and we have a weight m for which m at 0 is not equal to 0. Now we take t defined by composition and multiplication. In this case, the point spectrum is m0 times the point spectrum of when you remove the weight and moreover the spectrum is also equal to the point spectrum union 0. Okay, and in the case where the derivative at 0 is equal to 0, the point spectrum is m0, and so I had it. If the derivative at 0 is 0, but it is not a rotation, then the point spectrum is just M0, whereas the spectrum is just 0, 0 and M0. Okay. And moreover, because once we have a description of the point of the spectrum, the point spectrum, it's also very interesting to know if we can describe the eigen space. We can do that. Moreover, we have the existence of two functions. Say kappa and sigma, the one defined by Koenigs, which are unique to a constant of to a non-zero constant. Such that the kernel of T minus M0 phi prime 0 to be N identity is just a one-dimensional space generated by kappa sigma to the N. So again, it's one-dimensional. Okay, and the sigma, the sigma is the one by Koenigs. Okay, so I will give you the proof of that.
May I ask you one thing, Isabelle?
Yes.
So is it possible to write or to relate in a way the function k, or even the Koenigs, well, say the function k to the weight m? So is there any direct relation between both functions?
Yes. I will construct the function kappa and the function sigma. Well, sigma, we know what it is just because it's the one in Koenig's theorem.
Yes.
And the kappa, yes, I will give, because we will prove the point spectrum and we will see where kappa appears.
I see.
And it's really associated with the weight and the symbol.
I see. I see. Thank you.
Okay, so I will just reformulate the study of point spectrum in terms of functional equations. So, okay. So the way we study this is a reformulation of the point spectrum and the spectrum. In terms of functional equations. So to be in a point spectrum is equivalent to say that we can find a non-zero function such that n f composed with phi is equal to lambda f. for all z in D. Okay, and this is the same as saying that, okay, you can just, okay, just put a -0, minus here, and this is 0 for all z in D. And we call it, this equation is Schroeder, homogeneous Schroeder equations. So SH, like that. And to be outside the spectrum is in fact equivalent to say that for all given G, there exists a unique F such that M F composed with phi minus lambda F is equal to G. So this is a non-homogeneous Schroeder equations. Where lambda and G are the parameters, and we are looking for F. Okay, so let's have a look to the point spectrum and see where the function kappa appears. Okay, so maybe that the second part of the talk. So about homogeneous Schroeder equation. Okay, so we have this equation, M F composed with phi minus lambda F is equal to 0. And the first thing to do is just to identify the multiplicity of 0 as a 0 of F. It means that there exists an N, maybe equal to 0, such that F is equal to Z to the N times a certain F1, where F1 at 0 is not 0. So it's multiplicity of 0 as a 0 of F. Okay. And once we have done that, we replace in these equations, and we get M phi to the N, F1 composed with phi equal to lambda Z to the N G. No, G is F1. So. Okay, so we see that the lambda has the form n, so the weight times phi over z to the n. It's not g, it's f1, sorry. So f1 composed with phi to f1. at least where z is not 0 and z is not in the set of the 0 of F1. So now we take the limit as z tends to 0. Okay, so we get n is continuous, so obviously it tends to m of 0. This tends to phi prime of 0. And this is well defined because f1 of 0 is not 0. Okay, so this term tends to 1 because 0 is a fixed point and f1 is not 0, so it tends to 1. Okay, so the good candidates for the lambda point in the point spectrum have the form n at 0, phi prime 0 to the n. It's not difficult. Okay, so the point spectrum is included in the set of points of the form m at 0, phi prime of 0 to the n. Okay, so now in order to decide whether those points are in the point spectrum or not, we need to identify the function f. Because it can't be 0. Okay, so we have Tn f equal lambda to the n f for all n. And the difficulty now, because we have a weight, is to see what is Tnf. So Tnf is now more complicated than when we have a weight identically equal to 1, because now the weight has the form m. So at speed, it's m composed with phi, m composed with phi iterates n minus 1 times. Okay. F composed with phi composed n times. Okay. So we introduce a notation just to avoid to say all that. So phi n is phi composed n times with itself. Okay. So what happens for f? It follows that f is equal to 1 over lambda to the n times its terrible weight. So it's m phi n minus 1 And now I recall that we have introduced the function f1, which is the one with no 0 at 0. Okay, so using this notation, we have that f is equal to this times f okay, yes, it's phi n to the n times f1 at phi n of z. Okay, using this decomposition, we have that f is equal to that. Okay, and we also know that lambda is of the form n at 0, phi prime of 0 to the n. Okay, we put this in the equation, and so the eigenvector f has the form, if it exists, it has the form this weight over n 0. Oh, there's something wrong in my sorry. No, sorry, it's lambda to the n, so it's a power n here times phi n over the derivative at 0 to the n, big N, times g at phi n. Okay, so here is the good candidate for the only candidate to be an eigenvector for the eigenvalue lambda equal to that. Okay, and now everything works very well because, g is equal to f1. There is a mistake here. This g is in fact f1. Okay, so take the limit of this, and if it exists, we have an eigenvector. We have three terms. This one is easy because due to the dangeable theory, which is now a consequence of the Schwarz lemma, phi n tends to 0 uniformly on every compact subset of D. So it tends to a constant f1 at 0. That's a consequence of dangeable theory, or a Schwarz lemma in this case, because it's easy because the fixed point is inside. Okay, this one, that's exactly the definition of, that's in fact, the limit is the Koenig's functions. So that's precisely sigma. So to the big N, it's sigma to the N. So that's Koenig's results. Okay, and this guy, that's the new part, is now here. And you see that it is a combination of weight and obviously also on iterates of phi. And to make it converges, we will just use Weierstrass theorem. So this will tend to a certain function called kappa. And to do that, we use Weierstrass theorem. So all the limits are taken uniformly on every compact subset of D, because that's the topology we put on all D. And we prove that thanks to Weierstrass theorem. So we prove that this product converges because we just write it as okay, just write more details here. Okay, so the Weierstrass theorem we use is the fact that a sum of holomorphic function hk the convergence of this will imply the convergence of the product of 1 plus hk. And in our context, one plus hk is 1 over m0 m at phi k minus m at 0. Okay, and we're able to prove that sorry, it's not 1 plus hk, it's hk. Or maybe it's clear. Sorry, if so yes, it's hk and not 1 plus hk. And what makes the things works very well is the fact that the derivative of phi at 0 is strictly less than 1. That's the key to make to prove that that in fact we are able to prove that hk is less than a certain constant, the derivative at 0 to the k plus 1 on a compact. And so we can prove the convergence because we have a geometric series with a term which is strictly less than 1. Okay, so the function kappa, the second function, which is essential here, is the limit of this. So as in Koenig's theorem, we have sigma, which is the limit of that. So for a general phi, it's very difficult to have an explicit expression of sigma. And the same happens here. It converges, but an explicit expression of kappa is very difficult. Okay, now I will just give you an idea of how to prove that the spectrum is just a point spectrum union 0. Okay, so that's the third part of the talk. Strange, what happens? So we would like to solve equations like that, like this one. Where this is given. And we try to fix whether, for which lambda, and we can solve this equation for arbitrary g. So how to solve it? So a very naive approach consists in just saying that it's just Tf minus lambda f equal to g, where T is multiplication and composition. So if you have an arbitrary operator like that, just saying that T minus lambda identity times applied to F is equal to G, and you want to reverse this. So you would like to write that it's the resultant applied to G, which is minus 1 over lambda identity minus G over lambda minus 1 applied to G, and you get a series. So that's a very naive approach. Okay, so having this in mind, if you are allowed to do that, you find the solution. And you see the difficulty is that now Tn applied to a function is it's not so easy to manage because it's n composed with phi, n composed with n minus phi n over lambda to the n g phi n. Okay, so in other words, having a look to the naive approach, we can solve the equation if we are able to prove that this converges. So the problem is to find condition to make this series convergent. I will just give you the free step to do that. So the first thing to do is to prove, thanks to the fact that the derivative at 0 is strictly less than 1, we can prove But we have the convergence in very small neighborhood of 0. And what helps a lot is that we can find an integral such that the sum converges on a small neighborhood of 0, so the epsilon times the closed unit disk, and so the n0 appears here because we can do that for G in the set of functions which are 0 with multiplicity n0 at 0. So in other words, we can make it converges in a small neighborhood of 0 and for special G. So for the G in Zn0 or D. Okay, so we can manage to do that. So it's not for any G, but for the G in this space. The step 2 we show that provided we have a solution in this neighborhood, we are able to find an analytic continuation on the disk. So we show that the solution here extends analytically on D. But again, it's just for the G in this subspace of O. And the step 3, we show that provided the lambda is not in the point spectrum, and the point spectrum we have it. It's precisely all the point of the form m0 pi times 0 to the n. We show that provided the lambda is not in this in the point spectrum, then the non-homogeneous Schrödinger equation has a solution for all G using spectral projection defined by induction. So that the set of analytic function can be separated by the linear vector space generated by kappa sigma 0, kappa sigma to the n0 direction z to the n0 plus 1 or v. Okay, so that's the skeleton of the proof. And maybe to finish, I will show you what remains to do. So that's the idea of the proof. Some remarks. The first remark we can do is that when you have a T, a weighted composition operators, it's not difficult to prove that T is invertible in all D, if and only if the phi is an automorphism and the weight has no zero. So that's why. So when we have that phi is not a rotation because we have phi of 0 equal to 0, but we avoid this case. Phi is not an automorphism, and so 0 is obviously in the spectrum. It's automatic. The second obvious remark is that when we have an alpha in D, which is a fixed point, you can manage to prove that the spectrum is what you guess. So we also have the point spectrum and the spectrum. To do that, you replace 0 by alpha. So that's why we may assume that it is 0. So that's a usual trick in all this theory. Okay, and so maybe a few words about the case of a rotation. What happens when phi is a rotation? So this case is is much more complicated than expected because it really depends on the nature of beta. Case 1, if beta has the form 2ip times p over q, where p and q are integers. That is, if beta to the q is equal to 1, then in this case, you can identify the spectrum. Well, in this case, it also depends whether you have a weight or not, because it's possible to have, okay, so first, just mention what happens when you remove the weight. So even in this case, it's very interesting. So take a beta, which is, say, periodic. In this case, the spectrum of just the composition. So I remove the weight. The spectrum of the composition is the point spectrum of the composition, and you will recover this is a discrete set, and it will be 1 beta to the q minus 1. So that is not difficult and not surprising. But in the case where beta is say, aperiodic rotation. In other words, beta to the n is never equal to 1 for all n. Then the spectrum of C phi is quite difficult to describe. The only thing we can say is that it contains, obviously, all the beta to the n. So it's quite big because this is the dense set in the unit circle. But we can manage to find some special irrational here for which so we can find special irrational, say algebraic numbers, for example, or Johansen, and even more general, including some Liouville numbers. So we can find explicit, so for example, algebraic or Johansen number, for which all the point of on the unit circle of the form 2IP times a rational provided it's not 0. Okay. So we avoid 1 such that this is in the complement of the spectrum. So we have a dense set in the spectrum because when you have the aperiodic case, beta to the n is dense in the unit circle, but we also have a dense set which is outside the spectrum. And it's not possible with this definition of the spectrum, as the one we took at the very beginning, to describe precisely the spectrum of C phi without a weight. So it is the first case is put a weight equal to 1. It's really depend on the nature of the aperiodic beta. And okay, we also have some results about when you have a weight. It's quite technical, but when there is a weight and when you have a phi, which is a rotation, you separate the case where it is periodic and aperiodic. You can find some very special weights. You can describe all the weight for which the point spectrum is non-empty. In general, the point spectrum is empty. For the aperiodic case. And the spectrum is very different from what was previously. It may happen that the spectrum is unbounded. It can be the whole complex space, whole complex plane. Okay, maybe I should stop here.
Okay, thank you, Isabelle.
So there are questions.
Maybe I have one.
Yes.
Sure.
I guess you can expect. What happens if the danger point is on the boundary? For instance, if you have an hyperbolic self-map, okay, so that you have okay, something like an expansion and so on.
Many thanks for the question. Okay, so the story is completely different. When you just have without a weight, you just take a composition operators and assume that phi has fixed points on the boundary. Well, so it depends whether it's a hyperbolic or parabolic case. But in both cases, what happens is that the spectrum of C phi is, well, the point spectrum of C phi is the whole complex plane except 0. And the eigenspace are infinite dimensional. So, and then you can tell the end of the story in this case without a weight, because the point spectrum is as big as possible, and then the spectrum of C phi will be equal to the point spectrum, even only if the phi is an automorphism. Otherwise, it's the whole complex plane. And okay, the proof relies on deep result due to Valiron and Pomerenke. Well, you could, it depends whether it's parabolic or hyperbolic. And again, in this case, what is interesting is that for special weight, we are able to prove that when you had a weight, but not for all the weight, but we can say that for the situation is completely different because for some weight, for large class of weights, the point spectrum of MC phi is again as big as possible. What we don't have is a complete description of the weight for which you have this. And we also have examples of, so we have a description of N, such that we have that. And in fact, it really depends on the regularity of the weight at the interval point of phi. For example, if m at 1 is the interval point, it is not 0. And we also need that m is continuous in the neighborhood of 1. Then you have this phenomenon. And we have examples. We have constructed examples of weight such that the point spectrum is empty. So when you had a weight, it's really very chaotic. So, and I think it's nearly impossible to have a hope to describe all the possible weight for which you have this phenomenon without a condition of what happens in the neighborhood of the interval point. That's very natural, a very natural condition.
Mm-hmm.
Okay, so you see, when the interval point is on the boundary, the situation is completely different. Because without a weight, that's nearly the whole space.
Thank you.
Good. Thank you.
Are there other questions? Other remarks? If not, thanks again, Isabelle, for the very nice talk. Thank you.
Thank you.
We shall continue, Salmoniki, at the end of